Mass spectrometry is a technique that has a century of history and has been noted by several Nobel Prizes to initial discoverers and subsequent innovators. Always recall that mass spectrometry methods will only detect charged ions. What is specifically observed is a ratio of mass over charge, m over z. A notable aspect of mass spectrometry is the exquisite sensitivity. In many cases, only nanograms, even picograms of material are sufficient to get quality information. As a result, mass spectrometry is now an essential tool in characterizing biomolecules in a biological matrix, such as blood or plasma. The classical method is electron impact. This gives some structural information due to fragmentation. But what we rely on more these days are softer ionization methods, particularly chemical ionization, which gives us the molecular ion, and electrospray mass spectrometry, which has become particularly powerful for characterizing compounds that can form multiply charged ions. The invention of mass spectrometry is linked with the discovery of isotopes about a century ago. In this class, we will use the presence of stable, naturally occurring isotopes and the ratios of their relative abundance to help characterize molecular formula. Particularly useful is the ratio of carbon-12 to carbon-13. Carbon-13 is about 1% of naturally occurring carbon. The ratio of chlorine-35 to chlorine-37 in a ratio that approaches 3 to 1, and bromine-79 versus bromine-81, which occurs in very close to a 1-to-1 ratio. You are undoubtedly familiar with the atomic weight of the elements, which is a weighted average of the atomic masses of the naturally occurring isotopes. As mass spectrometry separates isotopes by mass over charge, it is the isotopic mass that must be used. Note that the isotopic masses are not integers except for carbon-12, which as a standard has been set to precisely 12 atomic mass units, or 12 Daltons. The deviation from integral values is a result of the mass defect, which arises from nuclear binding energy, decreasing the mass of the nucleus from its fundamental components. Protium has a nucleus of only one proton. The element also has one electron associated with it, and this is the mass of protium. There is no mass defect because the nucleus is only one component. With deuterium, which contains a proton and a neutron in the nucleus, note that the sum of the components of a deuterium atom is very slightly greater than the actual isotopic mass. And the difference is due to nuclear binding energy, which can be calculated by applying the famous Einstein equation E equals mc squared. For elements heavier than nitrogen, the mass defect actually causes the isotopic mass to be slightly less than the expected integral value. And this deviation can become quite substantial with heavier atoms, as shown with bromine and with iodine. Although there are computational programs that will generate many possible formula from exact mass data, I'll share with you a simple way of estimating molecular formulas for organic compounds, particularly those that contain carbon, hydrogen, nitrogen, and oxygen. First of all, consider that organic compounds are primarily composed of carbon and hydrogen atoms. We can generate a few alternatives, knowing that nitrogen of atomic mass 14 is equivalent to CH2, and that oxygen with atomic mass 16 is an equivalent for CH4. Then focusing on the digits to the right of the decimal point, which arise from the mass defects, we can make adjustments by estimating the number of hydrogens, which have a mass defect of approximately 8/1000ths of a Dalton. Nitrogen 14 has a mass defect of approximately 3/1000ths of a Dalton, and oxygen 16's mass defect subtracts 5/1000ths of a Dalton. This method can also be extended to estimate molecular formulas for compounds that have one or two elements with higher atomic mass. One clue is that the mass defect is often much lower than what we see for compounds that are dominated by carbon and hydrogen, sometimes even under the integer number, especially for the higher atomic weight elements such as bromine and iodine. In addition, the mass spectrum will often reveal chlorine or bromine atoms by a distinct doubling of peaks separated by 2 atomic mass units, with chlorine approximately a 3-to-1 ratio, and with bromine approximately a 1-to-1 ratio. Let's try these methods with a couple of representative data sets. This is a representative problem from the textbook in which I've combined data for the exact mass with the electron impact mass spectrum. This, in fact, is how you will typically see data presented. First of all, let's look at the molecular ion peak, which is an even number. That suggests that there are no nitrogen atoms or an even number of nitrogen atoms. The base peak is an odd number, which is consistent with a charged fragment. My preliminary hypothesis is that this compound has the elements carbon, hydrogen, and oxygen. Moreover, with the relatively large deviation from the integral value, the molecular ion probably contains quite a few hydrogens. Let's work systematically through the exercise. So if we divide this number by 12, this gives 9 carbons and a remainder of 6 hydrogens as our preliminary spectrum. So C9H6 is one possibility. We could replace the carbon with 12 hydrogens, make that C8H18, and that would correspond to a saturated hydrocarbon. We could also try some alternatives by adding an oxygen, which gets us to C7H14O. Another oxygen gets us to C6H10O2. If we now consider the mass defect, 0.1043, 6 hydrogens times 0.008 gives us 0.048, which is far too low. 18 hydrogens gives us 0.144, which is pretty high. 14 hydrogens gives us 0.112, which is closer. 10 hydrogens gives us 0.08, which is now getting a little low. If we modify the number for 14 hydrogens and subtract 0.005 for an oxygen, gives us 0.107, which is pretty close. And if you recall that the exact mass for protium is not 1.008, but slightly below that, then our claim is C7H14O. If we do the calculation for C7H14O, we will find that the calculated mass is 114.1045. That is clearly within 0.003 atomic mass units and well below the 5 part per million cutoff used by the Emory mass spec core facility. Let's try one that's a little bit more complicated. This spectrum is for a compound that has an exact mass that is slightly below the integral value of 170. What really stands out is that the molecular ion peaks have a 2-mass difference and close to a 1-to-1 ratio, with 170 being very slightly greater than 172. The molecular ion peak reveals that there is a bromine atom in this structure. The exact mass is for the lower atomic mass isotope at 170. Therefore, we subtract the isotopic mass for bromine 79 to get the remainder. Note that this matches the base peak fragment at 91. If we divide the remainder by 12, that gives us 7 carbons and 7 hydrogens as a candidate. 7 hydrogens is estimated to contribute 0.056 to the mass defect. You can see that this is now very close. And in fact, we can confirm the claim of C7H7Br by using the isotopic masses in the table. I'll conclude the video by showing the predicted patterns of various combinations of chlorine and bromine, which is taken from the textbook. What this is most helpful for is if you have 2 or more chlorines or 2 bromines, or on occasion a mixture of 1 bromine and 1 chlorine.